Have you ever just sat back and wondered how an AI can take a simple prompt, like a cute cat, and spin it into a stunningly realistic image, almost in the blink of an eye? I mean, it really feels like magic. But behind that magic is this incredibly powerful process. And for a long time, that process had one huge problem. It was just so slow. But what if the secret to making it faster wasn't some brand new invention, but just a deeper understanding of the tools we already had? Well, it turns out the answer was hiding in plain sight.
Okay, so at the heart of most of these AI image generators are what we call diffusion models. They work by starting with pure random noise, think of old-school television static, and then, step by step, they refine that noise until a clear image just emerges. And what you're seeing here is the start and the end of that journey. Going from that chaos on the left to the crystal-clear cat on the right is, let's be honest, an incredible feat, but getting there takes a massive amount of computer power and time. So the billion-dollar question in the field has been, how do we get this same amazing result, but in just a few steps, or maybe even just one?
So yeah, we have this serious need for speed. Diffusion models are absolutely revolutionary. No one's debating that. They've given us these incredible, state-of-the-art images. But the way they work, requiring dozens, sometimes hundreds of steps, is a huge bottleneck. This slowness is what's holding these tools back from being used in real-time applications, where you need that instant feedback. And that's exactly the problem a team of researchers decided to sink their teeth into.
To get around this speed problem, researchers turned to a really clever idea called model distillation. The concept is actually pretty simple, but super powerful. You take a huge, slow, but highly accurate teacher model, that's the one that takes 100 steps to make a perfect image. Then you train a smaller, much faster student model to produce the exact same quality image, but in a fraction of the time. The whole goal is to basically transfer all that knowledge and skill into a much more efficient package.
Now, one of the most promising ways to do this is a technique called Distribution Matching Distillation, or DMD for short. On paper, it's just beautiful. It's elegant. The theory is that if you can train the student model to perfectly match the distribution of all possible images the teacher model can create, then it's basically learned all a teacher's skills. It's a really solid, powerful approach that's produced some of the best results out there. But there was a catch.
Yeah, it turns out the beautiful, clean theory of DMD had a secret. In practice, to get the absolute best results, researchers were using a specific ingredient that, according to the original math, really shouldn't have been there. It worked great, but nobody really understood why, and it created this glaring inconsistency between the elegant theory and the messy, real-world results.
And that secret ingredient, it's called classifier-free guidance, or CFG. Now, if you've played with AI image generators, you might know about CFG. It's basically a dial you can turn up to make the model stick more closely to your text prompt, which usually gives you higher quality images. The thing is, everybody uses it. The problem is, the pure math behind DMD just doesn't account for it at all. So the very thing that made DMD work so incredibly well in practice was also completely breaking its own rules. And this leads us to the central puzzle of this entire story. How could a method get state-of-the-art results by using a trick that fundamentally violates its own principles? I mean, that's just weird, right? This disconnect suggested that maybe our whole understanding of why DMD was so successful was incomplete. Or maybe, just maybe, it was flat out wrong.
This is where the new research completely changes the game. It proposes this radical shift in perspective. The old way of thinking, on the left, saw DMD as just one single process, this distribution matching thing, and CFG was just kind of a messy but necessary hack you threw in. But this new paper proposes a decoupled view. It argues that DMD isn't one process at all. It's actually two totally distinct, separate mechanisms working together in perfect harmony.
And to explain this, the researchers came up with an absolutely brilliant metaphor: the spear and the shield. By mathematically breaking down the DMD training process, they found that what everyone thought was a single tool was actually two different components doing two very different jobs. And this, right here, is the key that unlocks the entire puzzle.
This slide just lays it all out perfectly. The spear is a component they named CFG augmentation. Think of this as the aggressive engine. It's the part that does all the heavy lifting, the part that's responsible for turning a slow, multi-step process into a blazing fast one. And then you have the shield. This is the original distribution matching part. And its real job, they discovered, wasn't to be the engine at all. It was to act as a defensive guardian, a regularizer that keeps the whole training process stable and prevents the super powerful spear from going wild and creating ugly visual glitches.
And this quote from the paper just nails it. The big takeaway is that the part everyone thought was the entire method, this distribution matching, is actually playing a supporting role. The real star of the show, the engine that's actually driving the incredible speed up, was this previously overlooked CFG augmentation. I mean, this completely reframes how we understand these models learn to be so fast.
Okay, so if this theory is right, what happens when you try to use one without the other? Well, the researchers designed a whole series of experiments to isolate the spear and the shield, just to see exactly what each one does on its own. And the results are, well, they're fascinating.
So first, they tried training a model with just the spear, that engine component. And on the right, you can see what happened. It's actually amazing at generating the image quickly, which confirms, yep, it's definitely the engine. But look closely. The colors are totally blown out, it's oversaturated, and it's full of these weird artifacts. It's powerful, for sure, but it's also reckless and unstable on its own. Now compare that to the image on the left, which uses both the spear and the shield. It's clean, it's crisp, it's stable.
Next, they did the exact opposite. They trained a model with only the shield, that defensive regularizer. And you can see the result over on the right. It's stable, sure. You don't get any of those crazy artifacts, but the image is blurry, it's washed out, and it's missing all of the fine details. The shield is safe, but it's also weak. It just doesn't have the horsepower to create a high-quality image by itself in just 1 or 2 steps.
And the data backs this up perfectly. This graph shows a quality score over the course of training. Now look at that green line. That's the spear all by itself. It shoots up, it learns really fast, but then it just completely collapses as the training goes off the rails. Now look at the gray line. That's the spear and the shield working together. It learns just as fast, but the shield keeps everything stable, right up at that high level of quality indefinitely. This is the smoking gun. You need both. You need the engine and you need the guardian.
Okay, so this is where it gets really exciting. This discovery isn't just some academic thought experiment. By finally understanding that the spear and the shield have different jobs, the researchers could actually figure out a smarter way to train them, leading to even better performance than the original method.
They created something they call the decoupled hybrid schedule, and the logic behind it is just beautiful. Since the spear is the engine for adding new details, they trained it to focus only on the parts of the image that are still noisy and unresolved. But since the shield is a global guardian, they trained it to always look at the entire image from start to finish so it could catch and correct errors anywhere at any time. They basically gave each component a job that was perfectly suited to its unique strengths.
And the results? Well, they speak for themselves. This table compares their new decoupled method to the previous best-in-class, DMD2. For metric like FID, where lower is better, they're lower. For metrics like clip score and image reward, where higher is better, they are significantly higher. They didn't just meet the state-of-the-art. Armed with this new understanding, they beat it.
And the visual proof is just as striking. Look at the image on the left from an earlier method. You can see that color over saturation we talked about. It gives the image a slightly greasy look. Now look at the image on the right from their new decoupled hybrid method. The details are richer, the colors are more natural, more realistic. This is the real, tangible result of training the spear and the shield in a smarter way.
So, what does all of this mean for the bigger picture? Because this isn't just about one algorithm. This discovery, this new way of thinking, has some pretty profound implications for the future of AI.
So why does this matter so much? Well, 3 big reasons. First, it pushes us way closer to truly real-time AI. Faster, more efficient models open the door to all kinds of interactive applications we've only dreamed of. Second, it just means higher quality. By understanding why these glitches happen, we can design models that avoid them from the get-go. And finally, it gives researchers a whole new framework, this whole spear and shield idea, to think about when they're building the next generation of AI models.
You know, when you step back, what's so cool about this story is that the breakthrough didn't come from inventing some brand new, super complicated algorithm. It came from looking closely at a method people were already using and just asking a simple question. Wait a minute, why does this actually work? The real secret was hiding there the whole time.
And this just perfectly captures the nature of science, doesn't it? We've solved a major puzzle. We now know how to build these incredibly fast models by treating the spear and the shield as separate entities. But in doing so, we've uncovered an even deeper question. Why is the spear so incredibly good at its job? Why does this specific mathematical trick have this almost magical ability to collapse a 100-step process into one? Well, that's the next great puzzle for researchers to solve.